Okay, welcome everyone to HAO Colloquium, the special colloquium today at 1:30. Our speaker is Samhita Chandra. He's a PhD student at the Max Planck Institute for Solar System Research in Germany, working with Dr. Robert Cameron and Professor Sami Solanki. She is using radiative MHD simulations MURaM chromospheric extension to the MURaM code, MURaM chip, to study fine structure in the solar chromosphere. She has developed a proxy for H-alpha using MURaM CHE. This proxy can be used to identify features in the wings of the H-alpha line and is being incorporated into MURaM CHE. She completed her integrated bachelor's and master's in physics from the Indian Institute of Science, Education and Research, Kolkata in 2022. Her master's thesis was using kinematic dynamo modeling to probe the solar magnetic cycle with Professor Divyendu Nandi. She studied the behavior of the solar dynamo with a special focus on solar grand minima episodes. She was a Department of Science and Technology Government of India Inspire Scholar during this time. She was also an Indian Academy of Sciences Fellow 2019 and Jagadish Bose National Science Talent Search Scholar 2015-2017. Besides running numerical simulations to understand the sun, she enjoys hiking, Indian classical singing and dance, reading and sports. To Shamita, and she will be talking today on probing chromospheric fine structures with an H-alpha proxy using MURaM.
Thank you for the introduction. So I am working on probing chromospheric structures with an H-alpha proxy using MURaM, and I'm working with, so my collaborators are mentioned here. I will now quickly talk about what I have been working on. So let's begin with the sun. So when we look at the sun, which is not recommended to look at directly, but the maximum radiation that we see coming from the sun is from the solar disk, and this is what you can see in this image. And once we start occulting this intense radiation coming from the solar disk or the photosphere, we start seeing the upper layers of the solar atmosphere, and that begins with the chromosphere. So in this image, what you can see as the red emission towards the limb of the solar disk is H-alpha emission, and it's basically denotes the chromosphere. So let's talk a bit about the chromosphere. The word literally means color ball, and it comes from the fact that this intense red radiation with which it was first observed, that happens to be at about 656 nanometers. And this is when hydrogen transitions from the n equals 3 to n equals 2 energy state. And this is what is the H-alpha spectral length. So this layer is very interesting and complex, and the chromosphere is out of local radiative and statistical equilibrium. And the dynamics also switches from being plasma dominated down in the photosphere to being magnetic pressure dominated or magnetic field dominated out into the corona. And this chromosphere is sandwiched between these two very different layers. And because of this, this is a very dynamic, very complex layer, and it's also very inhomogeneous. And that is also very evident in this image itself. So it is very difficult to probe this layer, both using observations as well as from a modeling perspective. But let's try to do this. So first, I am showing some observations using SST-CRISP, and this is in the H-alpha line. And in this movie, you can see there are these very fine needle-like structures, and these are typically known as spicules. So close to the solar limb, we can see these very fine structures, and they are quite ubiquitous. So in the H-alpha line, you can see them almost covering a major part of the sun. So in the chromosphere. And what is interesting and also complex about this is that we are looking at very small length scales as well as time scales. So these are very dynamic features, and they're also associated with short, small time scales of evolution. And here on the right, I show observations of spectral lines. So here I'm putting an emphasis on the H alpha line. And you can see how it looks like with, for example, FTS Atlas. And what I also want to emphasize is that this is an absorption line. So you see a dip in the intensity. And where the dip is maximum, this region is known as the line core. And when we move further out from this core, we come to the line wings. So this is, for example, the blue wing, and then this is the red wing. So this is observations. Let's talk a bit also about what exactly are spicules, or these RBs and RREs. So spicules are very fine multi-threaded structures, and these are visible close to the solar limb. And they are typically categorized into two types. So type 1 spicules are usually slower, and they have a parabolic trajectory in the time distance plot. So it appears to be something like when material is being thrown up and it falls back down. And these are typically slower fine structures. And the type 2 spicules are much faster, and they have a linear trajectory. So they're being it appears to be something like something is shot up, and then there's nothing that's falling down. So something like a linear trajectory in the time distance maps. And RBEs and RREs, or rapid blue and redshifted excursions, are considered to be the on-disk counterparts of these spicules. So that is something that you can see in this image, for example. And I am focusing on these on-disk RBEs and RREs. So to give some idea, the lifetimes of these features are few minutes, and by few minutes I mean something like tens of minutes and less. And the lengths are few megameters, again up to 10 megameters and less. Widths are hundreds of kilometers, and upflow speeds, for example, for our RBEs are in the range of 30 to 40 kilometers per second. And these are very dynamic fine structures, and they are not very well understood as to what role they are playing in terms of the energetics, how these are formed, and so on. But these are well visible in the wings of H alpha. So I will come to what I am doing. I am basically using numerical simulations to understand these features. And for this, I'm using the chromospheric extension of the MURaM code. So this MURaM code is 3D RMHD code, so radiative MHD code, and it's in Cartesian coordinates. So imagine you have the sun, and then you have a tiny box, and here you're solving for the equations and modeling the solar atmosphere. And MURaM is able to simulate the near surface convection. So for example, in this image, this is the near surface convection. It has been chopped out for better visualization here. And then we have the solar surface at 0, which is the photosphere. And we also have the corona up here. And there was the chromospheric extension was relatively new. So Damien Trybulski added this bit to the MURaM code, and so we have the chromospheric extension now. And here in the temperature profile, you see this region, which is the chromosphere. So this chromospheric extension has the non-local thermodynamic equilibrium physics to treat the chromosphere. And further, the hydrogen treatment is done in non-equilibrium. So if I play this movie, here you see the magnetic field as it would look on the surface. So this is the line of sight component. And this is an enhanced network. So there is an enhanced magnetic network patch that is visible in this region. And then I've taken two cuts, so two vertical cuts, and then that is the temperature profile seen here. And here you can see that there are many fine structures that starts appearing in these simulations. And this is a relatively more quiet region, but this kind of features motivated us to start looking at these fine structures. But MURaM itself cannot output synthetic observables. So if we have to compare with observations and see how well this model is working, we would have to rely on synthetic observables. So in order to do that, we also used the multi-3D code. So what this does is, so we take the MURaM atmosphere, we feed it into the multi-3D code, and then we can get an emergent H alpha intensity. So here on the top, again, I show the enhanced network. So this is the line of sight component of magnetic field at the surface. This is in the chromosphere. And when the MURaM atmosphere is fed into multi-3D, we get this kind of H alpha intensity maps. So this is somewhere in the blue wing, and this is in the red wing. And you can already see that there are fine structures which start appearing in these simulations. And this is interesting. But how well does this compare to actual observations? So just to give an idea, here on the left, I'm showing actual SST observations on disk. So these are RVEs. And on the right, this is the synthetic H alpha image from the multi-3D output. And by the looks of it, you can already see that it's quite similar in terms of the appearance. So the morphology, the locations, and things appear to be very similar in a qualitative way. We also wanted to check how the line profiles compare. So this is from FTS Atlas in blue. And then from the multi-3D MURaM for a particular snapshot that I just showed here, this is the profile that is shown in orange here. And you can see that although there are some discrepancies in the line core and far out in the wings, this is a reasonable match. So now something that's difficult with these simulations is that when we use multi-3D to produce this kind of maps, it is very computationally expensive. So for one particular one snapshot itself, it takes about 10 to the 5 CPU hours. And if we want to look at, for example, one particular feature and see how that is evolving with time, then it is going to be very cumbersome to use multi-3D and try to create all these maps. So what we wanted to do was to come up with a proxy. So that is what I will be talking about. So the first part is about constructing and validating this proxy. So here we have hydrogen modeled as a two-level model atom. So first we take the line profile. So this is what it looks like. And then we compute the absorption coefficient. And that is shown with this equation. So the n equals 2 and n equals 3 are the hydrogen level populations at these two levels. So this is the two-level model atom. And these are obtained from the non-LTE simulations from MURaM CHE itself. So then once we have this absorption coefficient, we then compute the optical depth. So that is given by this here. And then we compute this in the heights for most of the H alpha forms. And we have extended this further, and that does not change our results. So this is what we are working with. And then finally, when we have this, we model this H alpha as an escape probability. So this is what is highlighted over here. So what this is telling you is if there is a photon escaping from the photosphere, and what is the probability that if it travels a distance z, that it will successfully escape. So if this value is 1, then that means that the photon has successfully escaped. And if it is 0, then it is completely absorbed. So this is how we are developing this proxy. And this is what I also show here. So for a particular snapshot, the average profile looks something like this for the proxy. Now, how does this compare with the multi-3D synthesis? So here I will show you a scan through the line, and you will see features that start appearing in the multi-3D, synthetic H alpha, and in the proxy. And once I play the movie, you can see that in the wings, the features appear to be quite similar in both these maps. Once we move towards closer and closer to the line core, the proxy saturates, so it is not good at the line core. But again, when it comes into the red wing here, you start seeing features which are again very similar. So because we are focusing on these fine structures, this proxy suffices to be used for studying these fine structures visible in the wings of H alpha. But we wanted to take this a step further and check how good is this proxy working. So first, on the top here, I show the scan through the line again. And then what we do is we do a pixel by pixel analysis. So we bin the pixels in the synthetic intensity and the proxy into these 2D histogram maps that you see here. I can talk in greater details about this, but just to give a broad picture, what we do is after binning and getting these kind of 2D intensity maps, we then impose some thresholds to understand which pixels actually correspond to a feature. So there are 2 of these thresholds marked with the dashed line. So this is for the proxy, and this is for the synthetic intensity. And then as we move from in the line wings, we can see how this evolves. But using these intensity maps, we can now classify the pixels into 4 categories. So we have true positives, true negatives, false positives, and false negatives. And these are color coded in this map, for example. So here you can see the pixels as they would appear as, so as they're identified as true positives, true negatives, false positives, and false negatives. And then we further quantify this, showing the percentage of pixels which are for the entire map, which are true positives, true negatives, and positives and negatives. So I will now play the movie and show you how well the proxy is behaving. And you can see that it does a decent job. So we are identifying the true positives, true negatives quite well. And you can also see this positive trend. So one thing that I should also mention is that this on the left is the 2D histogram binning of the 2 kinds of pixels. And here we have normalized the same thing so that this trend is better visible. So this is basically row normalized of this map. So we can see that the proxy is doing a good job, and this gives us confidence that we can start using this proxy to study individual features. So coming to the conclusions of part 1, the proxy for the synthetic H-alpha intensity maps capture the position and the morphology of the features quite well in the wings of H-alpha. So this proxy works quite well in the wings of the H-alpha, but not so much in the line core. And this would be another step to take in the future to develop a proxy in the line core. But for now, we have this proxy which operates at a far lower computational cost, which is like few CPU seconds for each of these maps, compared to using code's 3D radiation complete intensity treatment of 3D radiation field with multi 3D, which takes about 10 to the 5 CPU hours. So this is a good speed up.
So, quick question: is the proxy always symmetric, or can it have asymmetries?
So you mean in the wings?
Yeah. Well, I mean, across the spectral line, is it symmetric about the core, or can it be asymmetric?
It can be. So the way the proxy is constructed, it is taking, so as I showed here. So there is, if you look closely, there is some asymmetry, for example, in this and this.
Yeah, takes the velocities. Yeah. Okay.
Okay.
Yeah.
Yeah. Oh, okay.
Thank you.
I have a question on the next slide.
Yes.
No, the next that you have pulse. Yes.
Yeah.
So the pulse positive, pulse negative are going closer to the true positive, true negative when the velocity is low.
Yes. So this is far out in the wings. So here, for example, it's doing a good job when it's far out at these high velocity double shifts. So the features are quite well identified. And then there is some departure closer to the line core. So as it moves to the line core, then this proxy starts saturating. So there is this departure. Okay. Yeah, we are also building this proxy into the code so that we can have these kind of H-alpha maps as a standard output. So now coming to part 2, now that we have this proxy, we want to use it to study a particular feature. And here I will be talking about just one feature at this Doppler shift of 37 kilometers per second, which is in the blue wing. So positive velocities are blue wing features and negative are red. So this is the overview of this particular feature that I'll be focusing on. So on the top here, you again see the proxy map of the entire field of view. And here, this feature is highlighted by the red box. So we are going to be studying this particular feature. And this is what it looks like in the synthetic intensity. And this is from MURT3D. And this formation height information is also what we obtain from MURT3D. And this is for this particular snapshot. So from the formation height, what it is telling you is where in the atmosphere is this feature forming. And from here, you can see that it forms at heights of about 2 to 4 megameters. So this is focusing on the on-disk view of this particular feature. But then we take vertical cuts. So this green line over here marks the base of such a cut, and then the vertical plane is out of the plane of this presentation. So then we start obtaining these vertical cuts, and this is what the feature looks like in the proxy with this in this vertical cut. So although it appears to be a straight feature in this on disk, it is actually it appears to be a sort of a loop-like configuration in this vertical cut. So maybe what we're seeing is tops of these loops when we see them on disk. So this is the vertical or the line of sight velocity. And you can see that this proxy is appearing in the upflow regions, which is consistent. And it also appears that this is rooted at this negative polarity patch. So this feature seems to be rooted in here. With this proxy, we can also see that it forms at about 2 to 4 megameters in this vertical cut in the atmosphere. And this is consistent with what we have from the formation height information using MURT3D. So it is actually identifying the correct location. Yes?
How do you show the proxy in height when it's an integral?
Yes, so yeah, thank you for the question. I should have mentioned, so this is essentially the normalized absorption coefficient, which I showed earlier. So when I'm talking about the proxy in the vertical cuts, this is basically this quantity, but normalized so that the feature stands out. Yeah, so this is the feature. This is the overview of the feature. And then we can look at the time evolution. So this is a 10-minute time series. And I have shown various quantities here. So you can see features in and popping in. Okay, I don't know why this is not running. Okay, I can try to play this again. Okay, it seems to have no response.
Go back one slide and then again it controls.
Yeah, it's happening on my laptop, but I don't see it here.
Oh,
Maybe try to stop sharing.
presenting.
Okay, yeah. Okay. So yeah, so if in this evolution, you can see features popping in and out in the vertical cuts. So all of these panels show vertical cuts through the green line as the base. And you can see that there are features that are appearing into the view. Okay. And then this is the feature which appears first. It appears out of this plane, which is marked by this green dashed line, and then it moves into this plane and then further moves out in the left. So, okay, I hope this plays now. So wherever the features appear, you will see it appearing in upflow regions in chromospheric temperatures and are enhanced in the hydrogen N=2 populations. So here now you can see the feature appearing and then it moves into the view. And here you can see that there is a positive polarity intrusion associated with the feature when it first comes into this plane. And in this predominantly negative polarity region, when the feature comes into this plane, there is a positive polarity intrusion. And this made us question whether there is some flux emergence and magnetic reconnection happening there. So I can show this in detail again in another view. But so we wanted to check what the magnetic field line configuration is. And this movie shows what it is close to the birth of the feature. So this, we can see two bundles of field lines. So one is this overarching bundle, which connects somewhere in this region. And then there is a secondary bundle, which curves and comes into this view. So what we think is this negative polarity intrusion, positive polarity intrusion that we were seeing is because of this. And that is happening because there is an additional flux emergence, and there's something going on here. And we wanted to investigate further what is happening here, because there is field lines curving into this plane, and then there is also polarity inversion here. So let's look at the evolution of the magnetic field, line of sight magnetic field. So this is at the surface, and this is in the chromosphere. And you can also see the evolution of the features. And what is important is these features appear to be rooted at the magnetic network. So all the features that we see here appear to have their roots embedded in this magnetic network patch. And this is consistent with observations. So in this red dashed box, I highlight where the feature is essentially forming and evolving with time. So initially there are some features appearing in the vicinity, and then at some point this feature starts to take shape, and it moves in a leftward direction as it evolves. So let's have a closer look. So now I'm zooming into this red dashed box that I showed earlier. Now, if you focus on this part, so this is again magnetic fields at the surface and the chromosphere. And this starts out with positive polarity predominantly. And then as time evolves, there seems to be flux emergence and cancellation, and this converts to a predominantly negative field. And that extends even to the chromosphere. And once this happens, the feature starts to form. And this is also shown in this particular panel, overplotted. And then it kind of wobbles a bit and then disappears. So this is focusing on the features. So there is some signature of flux emergence, flux cancellation, and reconnection.
So that pink feature, that is, you are plotting BZ, and is that XY horizontal? So is it a projection that you are seeing? That pink feature?
So the pink feature is the line of sight integrated proxy. So, and that is overplotted on this. So yeah. So now we wanted to move to the field line carrying this feature. So now we will start tracing field lines which pass through this feature and try to look at the evolution. To give an idea of what this looks like in 3D. So for this particular point in time, the field line looks something like this in 3D. And then this green line is again for reference. It is the same green line as you see here. So if we take a plane through this field line, a vertical plane, then we start getting maps like this. So this is basically a curved base, and then we extend it to height, and then we start getting these kinds of vertical cuts. So now we want to look at various properties of the feature in the plane of this field line. So this is the field line carrying the feature at this particular instant, which I have been talking about. And it is enhanced in hydrogen N=2 populations. Again, it's in upflow regions. There is nothing that stands out in the chromosphere temperatures that characterizes this. And it is, again, rooted at this negative polarity foot point. We also checked the viscous and resistive heating, and we find some signatures of heating also associated with this feature. So let's look at the time evolution. So initially, there is some flux emergence that you could see here. And then there is a field line. The field line itself also moves upwards and outwards. So once this feature forms, we can look at it again. So in the beginning, so at this point, there is this flux emergence, which is about at this distance. So this magnetic field moves up, and then the field line itself also kind of moves up and expands. So we think that there is a flux emergence that is driving magnetic reconnection. And you can also see strong signatures of heating associated in this region. So to give a different view, this is some time-distant plots of the feature and some of its properties. So this the vertical axis here is time. So you can see the evolution of the feature in this view, and this is what it looks like. And if you look at the gas pressures and the gas density, you can see local enhancement of the pressure and density in the region of the feature. So that is interesting. The temperature, however, does not show such a something that stands out. This is what the viscous and resistive heating looks like. And we also have plotted the divergence of flows. So in the region of the feature, we can see that it is dominated by compression. So the plasma is being compressed in this region of the feature. And there is enhancement of pressure and the density. What is also interesting is that we find an oscillatory behavior of this feature as it evolves through time. So, and this is much beyond the foot point shuffling at the photosphere for this field line. So this is quite interesting, and it is quite evident in this time-distant plot. Also, what's interesting is that at the birth of the feature, so when it's becoming very prominent, there is a strong heating associated with it. And if we take the slope here, it corresponds to speeds of about 100 kilometers per second. And if we go back to the simulations and calculate the galvanic speeds there, that also corresponds to 100 kilometers per second. So we see that there is a heating front which is propagating at galvanic speeds in this for this feature. We wanted to take this a step further, so we will now move to the frame of reference of the field line itself. So for that, we have this new basis. So this direction is so tangents, normals, and binormals. And how would this look like for our field line? So this was the traced field line for the feature. And so this is the main foot point of the feature, which was the negative polarity patch I have been talking about. And the tangents are directed away from this foot point, so along this field line. And then the normals are always directed outwards and upwards, so and general outward direction. And the binormal component is always coming out of the plane, so towards the viewer in this view. And just to give some idea of in 3D, so this was the field line which has been shown here. So for better understanding, it might help to visualize this axis as roughly the y-axis. So this base is roughly the corresponding to the y-axis. So now we project the velocity in the tangent, normal, and binormal directions and have these time distance plots again. So in the region of the feature, if you look at the tangential component of the flows, then there is a strong, so there are positive velocities associated. So what this means is that there is a flow component which is driving the feature away from the foot point, and that makes it behave like a jet. And if we look at the normal component, this region again is dominated by positive flows, which means that there are flows acting on the field line, which is making it move upward in a general upward and outward direction. And for completion, we also have the binormal component, and this is what it looks like. And just to, again, emphasize that this is the directions we are talking about when we talk about tangents, normals, and binormals. What is also interesting is, so this feature itself has a propagation speed of 38 kilometers per second. And if you remember, we've been talking about a feature which has a Doppler shift of 37 kilometers per second. So this is connected with the mass flows. But we also find another propagation front here, and that is at a higher speed, and that corresponds to sound speeds of 50 kilometers per second in this region. We looked at the pressure gradients as well. So this is again the tangent component, normal component, and the binormal component. So if you look at the tangential component, it is dominated again by positive pressure gradients, which is to say that there are pressure gradients driving this flow, which is making this feature behave like a jet. And again, the normal, it is pretty similar for the normal component. So it is again dominated by these positive forces, which means that this pressure gradient is also driving flows, which makes the field line move upward and expand. And this is the binormal component. So there are some, there is some domination of the negative forces over here, and these might be responsible for the lateral motion of the feature that we saw earlier. But this still needs to be investigated further. So now I will wrap up with the findings. So the feature that we saw has properties similar to an RBE, and we find many such features using the proxy which are rooted at the magnetic network. And this is similar to what we see in observations. And the feature is observed in the blue wing and has these properties. And the driving mechanism is flux emergence and consequent reconnection. So there is flux emergence close to the foot point, and that pushes the field upwards, and that causes it to expand. What happens then is that the plasma is compressed locally, and that has gives rise to pressure gradients, and that drives these flows which make this feature behave like a jet. And there are also flows pushing the field line upwards as it expands. There is viscous and resistive heating at the birth of the feature, and that propagates a heating front at galvanic speeds. There's also intermittent heating at the foot points of the traced field line. And this is the future work. So I'm now incorporating the proxy into the chromospheric extension of MURaM. The next steps would be to perform statistics on how common these features are. We would also like to see if they actually correspond to what we see as PQs. So that could be done with devising the proxy with a different viewing angle. And we can also apply this proxy to study features in a larger flux emergence simulations. So this is a movie to show the existence of these features in the simulations. And with that, I would like to thank you.
Thank you. Okay, so now you can ask your questions, and the online participants, you can either raise hand or unmute yourself and ask your question.
I had the question about, it's easy if you go back up a couple of slides. Yeah, that one works. So is the x-axis on the top plots there, the distance, the same as the x-axis on your proxy plot on the bottom right?
So so this is the distance. So if you take this field line and flatten it down, so it is this,
yeah, okay. So
this is basically flattened and stacked in time.
Yeah, and that field line changes in time.
Yes, yes, which is why there is this region, which I didn't talk about.
Okay, understood. So that oscillation then in the kind of magenta highlighted part is not the foot point itself moving, it's more as material like moving back and forth, up and down.
Yes.
That field line.
Yes,
Okay.
so I can also highlight that again. So this is quite visible in this movie, for example. If you look at the feature, so it will appear in this region. So now it takes shape, and then it kind of moves up and then comes back down. And then there is this kind of back and forth. And I've gone back and checked the foot point motions, and they don't move as much. It's the feature itself that's doing this.
Other questions?
Will you just show the plot again where you were being shown the pressure kind of thing, and before that was just a velocity plot? Just go back just once. Yes, this one.
Okay.
So here you do have the velocity and also the pressure kind of thing. And so in one of the plots, you were like, I got like two questions in advance. So the first one is about like when you say that it gives an impression that the plasma is being lifted up. But again, with the specules and the chromospheric features, nowadays there is this kind of belief that the magnetic field and the plasma are not completely aligned. But since you're having some sort of a proxy in H alpha, can you see if there is some sort of an alignment between these two, or they're complete? There is some sort of a misalignment between these.
So in terms of how I do the field line tracing, I actually go into the density feature and then trace the field line which is carrying it. So,
okay.
So it is devised in a way such that I always get the field line which is primarily carrying the feature.
So you always get the features which are completely aligned with the magnetic field.
Yes, I am always following the field line which is carrying which is aligned with the density feature primarily. So, for example, here this feature is like it's a bit complex, but I trace the field line such that the majority of it is aligned with the field line that I'm tracing.
And second, where you showcase these oscillatory features. So you do have these oscillations, like I mean, with the velocity, I can see like red, blue kind of a trend, which is like if in terms of a simple wave, it could be like the feature is over the time going away, coming back. Also, you do have the pressure perturbation, the density perturbation. That means it could be the cross-section width is being varying and the density plasma it's also been varying. So like, okay, there's a very complex, generally that's what happened with these peculiar features. You do have cross-section width variations and the transverse motion as such. So in your simulation, are these being injected at the foot point motion as a wave? Or as you've been saying, there's no foot point motion, then is it just a characteristic of the jet itself? Like as the plasma will move up along the magnetic field line, it will kind of displace the guide and also make these cross-section width variations. What do you think?
I think it is this characteristic, as I said, is stands out from the foot point motion. So I think it's the plasma itself that is doing this. But in terms of if there are waves driving, so associated with this feature, there could be some contribution from the waves in the simulations, which is like from the surface, let's say PMOs. But I cannot say with certainty what exactly or how this is coming into play. Okay. What I can say is that this oscillatory behavior, for example, that you see here, is over and beyond the foot point motion. So this is actually the plasma doing this by itself.
Okay. Makes sense.
What's the you see that there's some belief that the plasma and the magnetic field are decoupled? What would physically cause that? Why would they not just follow the line?
I mean, at least with the H alpha, like there was from Bifrost, there was this paper from Martin and Sikora, and they were talking about the chromospheric features of decoupled, and there were observations as well coming from Andres. I don't know for his paper that he said there is some sort of 16 up to 16 degree misalignment between the observed feature, that is the intensity that you generate, and if you do a polarimetry, you can see what actually happened. So there is some sort of, and that's where this question comes in, that are these features really good to study waves in the first place? Not. Because we're just looking at the intensity, and what we just want to see is we have been tracing the motions of the magnetic field itself. But if they are not one-on-one, that means we might not be. So one of the ideas from Martin and Sikora's paper is that the features are there and the magnetic field kind of goes through them. So like over the time of one feature, it can change multiple magnetic field lines. It won't be very stationary one to one. So that is the idea.
So one way of going about that, at least with these kind of proxy, I would think that if we do it at a different viewing angle and then do the same analysis again, that could give some insight into answering that question.
Yeah, because that would be very interesting to see, because you are looking at a proxy of H alpha. And the H alpha, that is the kind of the question that actually popped up. Like, are we really tracing, like the intensity features that we look, are these really tracing the magnetic field, or they're not always in the same magnetic field?
Okay.
So yeah.
Hydrogen is very weakly magnetized. It's a tracer for plasma bulk movement, not a tracer for magnetic fields. You need heavier elements with higher ionization stages to actually do the to apply the Alphen theorem and say the flux is frozen, the magnetic flux is frozen in the plasma. When you're looking in hydrogen, it's very hard for hydrogen to track magnetic field lines because it doesn't magnetize enough.
Yeah.
And those Martinez Segura simulations he's got the ion neutral interactions, right?
Yeah.
The paper from Andres that you were referring to, I think was 85.2 or something like that.
Yeah.
So it's not even that, is that your emission is not necessarily happening along the field line.
Yeah.
So
that's where the question comes in, like why they are decoupled. I mean, with H alpha, okay, it's neutral. But again, is it just because it's neutral, it is decoupled, or it is anything collisional, which is like trying to getting along, or even if it is ionized, it's a calcium ion, and it's showing not 101, then okay, I mean, why?
Other questions? Anyone from online? Okay, if not, let's thank our speaker for a very nice, excellent talk.
hand raise.
Yes, please go ahead with your question.
Maybe it's
Muted.
Okay, thank you again.